And welcome back. All right, so what we got here today is local linearity and differentiability. Actually, mainly differentiability. We kind of talked about what it needs to be for a derivative to occur. In other words, what needs to be differentiable a little bit. We kind of talked about it in the forms of slope from the left not meeting the slope from the right. So we're going to go in a little bit more detail as far as when does a function not have a slope. In other words, when is it not differentiable? Differentiable means it does have a slope. And one of the things that we're going to do is we're going to take a look at local linearity. Local linearity is said to happen, okay, when I zoom in on a function and I get a straight line, okay? So let's go ahead and take a look at what that looks like. So I have a couple of functions here. I'm going to go to my calculator, and my calculator's got these already put in for us. And if you need to pause the video right now so you can go ahead and put these functions into your calculator, okay? They're on your notes, except for the last one. We'll talk about that. And what we're going to do is we're going to come over here. We're going to select the first one, and I'm not going to worry about the second two. All right, so I'm going to take a look at absolute value of x plus 1. If you don't know how to get the absolute value of x, you're going to go ahead and you would hit math, scroll over to number, and there it is, the first one, absolute value. All right, so I'm going to go ahead and hit graph again, and we'll see the absolute value of x plus 1. And then you should have that graph already kind of pictured in your brain of what that looks like. And what I'm going to see is what I want to do is I want to zoom in here at 0, 1. So I'm going to go ahead and zoom in, that's number 2. And I'm going to move my cursor up to where about 1 is. And I'm going to say start. I'm going to start zooming in. I'm going to keep zooming in. I want to zoom in close. Zoom in close as I can. And I might have to readjust up a little bit so I can keep my cursor on top of that point. I want to see what happens. Do I keep going in? I keep going in. I'm going deeper, deeper. I want to keep going. I want to keep going, keep going, keep going. Do it about 6 times total. Okay? Notice the graph isn't changing much here. Look how small this is getting. Each little change is so small. Keep getting smaller. Do you see my graph changing at all? I don't see it changing that much. I keep zooming in and it's not changing. All right. So I wonder if it's differentiable there. Maybe. We talked about it earlier, okay? So let's go ahead and let's look at my other function, okay? So I go back here to y equals, and I'm going to turn this one off, and I'm going to turn the other function on, the square root one, okay? And I turn that one on, and I'm going to push zoom 6. Zoom 6, why? Because I want to go back to the beginning. I want to see that this graph looks a lot like the absolute value graph that we just got done with. But I'm going to zoom in, see what happens. All right, so here I go. I'm going to zoom in, zoom, 2. I'm going to do the same thing. Remember, move my cursor up to that 1, where I think 1 is, and press enter. And I keep pressing enter. Okay, readjust, readjust, press enter. Again, we're going to do this about 5 or 6 times here, so that's number 2. Readjust, there's 3. Getting closer. Uh-oh, this is already starting to look different. Readjust here. And zooming in, there's 4. Oh. Do you see where it's starting to get to be like a line? Here's 5. It's flattening out. I'm zooming in closer. Gotta readjust. Uh-oh, went too far. I readjust to press enter again one more time, and now I can start seeing the line. Here it is. And this is what it means to be locally linear. Okay? It means that eventually when I start zooming in, when I get all the way there, I'm going to make this look like a line. So then the question becomes, what about the absolute value graph? I zoomed in a little bit further on this one. What is it going to look like? So I go back to y equals. I go and put that one back on, and I hit graph. There it is. The absolute value graph is still there. It still forms that V. The other one's got a flat line. So the second one, the square root function, is what's called locally linear. I was able to follow my line. Therefore, it's differentiable, whereas the absolute value one is not. All right, so we just got done with that graph. So let's go ahead and take a look at our next graph that we're going to go ahead and do. And it says we want to graph and analyze what is happening for the cube root function at x equals 0. So let's again zoom in several times. We want to see what is true about the tangent drawn at x equals 0. So I'm going to go ahead and get my calculator back out. And I'm going to come over here and I'm going to go to y equals. Notice x, the cube root of x when I do that. Okay, cube root of x. That's x's to the 1/3 power. Okay, hopefully you remember that. Summer, right? Summer packet. So here we go. I want to zoom 6 because I want to get back to my standard so I can take a look at what's happening first. I forgot to select it, I guess. So let's see what happens when I go back to y equals. Yes, I forgot to select it. So I come back over here and hit enter. Now I can go to graph. Now here we go. So I gotta see what's happening at 0 right here. So again, I want to go to zoom, and I'm going to zoom in, and right there it's 0, 0. So I zoom in. Here it comes. Ooh, straight there. Okay. Well, what's happening? Let's go and zoom in again. Zoom in several times. Ooh, what's happening there at that point? I zoom in again. Oh, you can kind of see if I zoom in one more time, I'm going to get a straight up and down line. So now you got to think back to algebra 1. What happened with a tangent you had, or a line that was straight up and down? What was the slope of a line that's straight up and down? That's right, it's undefined. Okay, so it's another possibility for me not to have it'd be differentiable at a point. Okay, so let's go ahead and sum this up. So summing up, okay, in summing up, here's what I can say, that I am not differentiable. So you can come over here and say, just put up here, I am not differentiable, D-I-F-F, okay, when there is a corner. So in this particular case, I am continuous, okay, but there's a corner. All right, that's when I had the absolute value. This one over here also looks like a corner, but it's something special because it's not as drastic as a change. It forms a nice little cup-like thing. So again, this is continuous. This one over here is continuous, right? But it has a cusp. So again, this is not differentiable. And again, the cube root of x is continuous. We don't have a problem with that. But it has a vertical tangent. When it has a vertical tangent, my slope is undefined, so it's not differentiable. Last but not least, something is not differentiable, okay, when I have a discontinuity. ITY. Okay, so when I have a discontinuity, I can't have a slope because I don't know what my slope is here because it's not continuous. All right, so it's kind of a hint. You need to be continuous first in order to be differentiable. Okay, so next, that's a key point. We'll come back to that later. Okay, so here are some characteristics that destroy differentiability. Sharp turns like corners and cusps that we just talked about, vertical tangents and discontinuities. Very important. Okay, that's why it's all pretty and orange. Okay. So now let's go ahead. I want to do this. I want to show it from a point. So we're going to do the exact same steps that we did from last one. Okay, 3.1. Okay. But we want to compare the right hand and left hand limits at point P to show why a function is not differentiable at P. Okay, and it gives the right hand limits of my slope. So from the let's do the easy one. Let's do the one from the right. When I'm coming from the right, what's my slope? Okay, I don't even need to do the whole limit thing, right? Because why? What's my slope everywhere on that one as I'm coming from the right? Should be 2. My slope there is 2. Okay, so now I'm going to go over here, and I'm going to find out about the left side. The left side, I do need my limit. The limit is h goes to 0. Okay, f of a minus h, or a plus h, excuse me, minus f of a all over h. In this case, my function here is going to be the square root of x, and I'm going to go ahead and plug that in. So it is going to be, excuse me, the limit as h goes to 0 of square root of x. So in this case, a is going to be 1. So the square root of 1 plus h minus f of a, well, f of 1, square root of 1 is just 1, all over h. This looks vaguely familiar. Again, my steps are as I plug in. If I plug in, I'm going to see I get 0 over 0. I can't factor it, so I need to multiply by the conjugate. So when I multiply by the conjugate, my conjugate's going to be 1 plus h plus 1 over the square root of 1 plus h plus 1. When I do that, my limit is now going to be, as h goes to 0, of 1 plus h minus 1 all over h times the quantity square root of 1 plus h plus 1. And so now what happens are my 1's will cancel. All right, 1 minus 1. My h's that are left over will go away. And what I'm left with is going to be equal to the limit as h goes to 0 of 1 over square root of 1 plus h plus 1. And h goes to 0, so I have the square root of 1 plus 1. Square root of 1 is 1. So this is going to be equal to 1/2. So because I've done that, what I've shown is that my left-hand slope is 1/2. My right-hand slope is 2. It's not differentiable. Okay? So there's my proof of it. There's my reasoning. It's not differential at that point because the slopes from the left and the slopes from the right do not match. Okay? Let's see what's next. Alright, so in this exercise it's asking us to find out what domains is it differentiable and which domains is it continuous but not differentiable, and C where it's neither continuous nor differentiable. Okay, so for part A they want me to know where it's differentiable. I want you to do these. So in this regards I want you for A, where is it differentiable? So that is, where is there no sharp turns, no discontinuities, okay, no vertical tangents, okay, where does that happen? Okay, that's going to be for part A. Part B is going to ask you, where is it continuous but not differentiable? I'll give you a hint, there's nothing in this one for part B. Alright, part C, where is it neither continuous nor differentiable? Okay, so where is it discontinuous? I'm going to go ahead, pause the video. You guys can go ahead and check your answers when we're done. Here we go. And boom, there's your answers. Okay, so this -3 less than or equal to x less than 0. So this part of my graph is differentiable because there's no sharp turns, no graphs, no cusps, no vertical tangents. Okay, this one here, same thing. This one is no vertical tangents, no cusp, no corners, okay, no discontinuities, so it is differentiable for this whole section. The only place where it's not differentiable is the same place where it's not continuous. That's for part C, which is when x is equal to 0. Alright, there's your lesson. Here's your homework. Okay. Oh, I was wrong. Okay, so on this one I want to go ahead and graph this. So take a moment, put this in your calculator. Inverse tangent, you're going to hit shift, second tangent, and that'll be your inverse tangent. Take a moment, put this in your calculator, and you'll see the graph here shortly. Alright, so here's the graph of inverse tangent. what I've done, I've zoomed in, and my window is at -1 to 1, and my y is from -5 to 5. So here's the inverse tangent of x. So I need to find out what's happening. So I want to find out, what's happening here, because what my function says is that for inverse tangent of x, x does not equal 0. It's going to be inverse tangent when x does equal 0, it's going to be 1. Okay? So when I go ahead and I take a look here, it appears that when inverse tangent x, it's 0, 0. But I want to go ahead and make sure, so I'm going to check my table. So I check my table, and what I notice is, yes, it is 0, 0. Oh, okay. Well, what I do know is because of my function, okay, at inverse tangent of x, my y value is supposed to be 0. But this function is telling me that it's going to be 1. So what I end up having is a graph that now looks like this. Okay, and because I have that, what's my reason why that's not differentiable? Okay, this one here, discontinuity. All right, there's your steps for it. Now you have homework, and here it is. And I look forward to you guys watching it and answering the questions. Please, let's get this done. Got the last section before the 6 weeks test. Bye.